Good morning, everyone. Today, I'm so glad and honored to be here among industry peers and friends to talk about two of the most critical topics facing our times, sustainability and AI. Both these topics have a common macro theme of impacting our future lives. Both these topics are also intertwined by the fact that each is dependent on the other to make our lives richer and to help us achieve our common goal of enriching the lives of millions. Now, sustainability has always been a nice to have, but not anymore. It has now become a must do for all enterprises. And there are several reasons for that. Number one, the global energy prices have almost doubled over the last 2 years. Yes, maybe because of the ongoing geopolitical tensions in Europe. But other than that, what we have seen is that the gas prices have also quadrupled over the last 4 years. So we see that trend of higher energy prices to continue at least in the near future. The second is environmental. There is no slowdown of energy-related emissions. And there is much to do if we have to meet the recommendations set by the UN panel on sustainability. And it's not just about energy-related emissions. It is also about precious resources such as water. A typical data center of 100 megawatts uses 1.1 million gallons of water every day. And I repeat, 1.1 million gallons of water every day. So apart from the environmental factor, the third reason why sustainability has become such a critical topic is because of the regulatory pressures, and thankfully so. So, for example, in the European Union, we now have standards published for capturing sustainability data and reporting sustainability data. So it's just like every enterprise has certain accounting standards that they have to follow. There are also now sustainability standards. And it's not just restricted to European Union. The other day I was talking to a customer in Thailand. And so it's in Thailand, if an enterprise now has to go to a bank for a credit, the bank evaluates the sustainability score of that enterprise. How sustainable is that business before they can advance the credit to that enterprise. So if we look at, where is sustainability when it comes to IT or our space, and if we look at specifically around servers that make up our data center. So if you see from a server standpoint, the embodied carbon, or the carbon which is because of the manufacturing of the server parts, such as the CPUs, the GPUs, the memory, that's the light blue graph that you see on the screen on the right. So embodied carbon is only 10%. 90% is the operational carbon, which is the carbon footprint because of running of those servers, when you put a workload on those memories, on those CPUs and GPUs. Whereas when we look at the handheld devices, the laptops and the notebooks and the desktops, it's completely opposite. The embodied carbon is a big part. The operational carbon is relatively lesser. So what does this tell us? That we have to work across. We have to make sure that we reduce the embodied carbon, and that is, we adopt sustainable manufacturing, and at the same time, we reduce the operational carbon as well. And this is where I'm proud to say that as Intel, some of our latest products are manufactured with more than 90% renewable energy. And we are net water positive in 2 of our main manufacturing sites. So the point is that when you buy an Intel-based product, your embodied carbon is reduced further. Now, switching gears, and if I talk about AI, in fact, when I was going through the slides this morning, I was not sure if I should have this slide because it's like preaching to the choir. Yes, AI is very important. Yes, every communication or every customer meeting that I'm having these days, it's all about AI. In fact, if there is any day where I don't talk about AI, I start feeling FOMO. So there is a lot. Everyone wants to do AI. Everyone wants to, automate their business processes. Everyone wants to solve real-world problems, right? And it's not just about, talking about AI. It's also about there is a real business which is happening in AI. So this is Gartner's prediction that the AI chip revenue is expected to be 53 billion by the end of 23. And we all know who is getting the majority of this chip revenue. Definitely not us at this moment. So while this is all good, the AI is making great progress. We are solving real world problems. However, there is a cost of this progress. Just to give you, another statistics, from 2012 to 2019, the rise in the demand for compute power has always been 300,000 times. So this is an era. So I'm talking about 2012 to 2019, the days of ResNet 50s and the days of Mascar CNN. The transformer models have not yet landed here. The cloud has not become cloud yet, right? So this is 2019. It's 300 times that the demand of compute has increased. Just one training of a transformer model is equivalent to 41 round trips from Sydney to New York. That's the impact, environmental impact that we are talking about. Okay. And of course, I'm sure, if this is the fact, then the question will be, what about our favorite GPT-3? So we took two models, equivalently large, equivalently big. GPT-3 and Gopher. Very large models solving really models, revolutionizing how AI is being perceived. But as we all know, a training for one GPT-3 or a Gopher takes thousands of megawatts, right? Now, that does not create the impact. Okay, so what if it is thousands of megawatts? If we translate this into carbon emissions, we are talking about 300 to 500 tons of carbon emission. Now put this in this context that this dwarfs the average carbon emissions of a car in its lifetime. So that's the impact that we are talking about when we train these large language models. So of course, one of the questions that all will come to your mind, oh, this is training. It's just once in a blue moon, it's once in a year. Fun fact, GPT-3, when it was launched, got 10 million queries in its first week of launch. So inference, although it's smaller, but the volume is bigger. And this is where we tested with Google, what is your ML energy consumption across training and inference. And as you see, 60% of Google's ML energy consumption is inference. So we just talked about the training, inference is even bigger. And this is the same trend across Meta, across other large enterprises that we have talked about. However, I still want Netflix to give me correct recommendations. I still want the Google Maps to tell me the accurate time every time. I still want all the benefits. I still want Copilot to be able to run on my laptop. I want all those facilities. I want to solve the business problems. Because yes, AI is solving our business problems. AI is making our life much easier. But at the same time, I want to make sure that this planet is still livable for my children and for his children. So how do we find that right equilibrium where we can continue with this process of digitization, we continue getting all the benefits, we solve the real problems, but at the same time we are conscious, okay, what is the impact on the environment and how do we make sure that we get the best of the both worlds? It's not easy, and again, there is no one right answer to it, but it's just that as Intel, we have certain thoughts and ideas as to how this can be done, and that I would be sharing in the next course of slides. So the first thing that, again, this is again what we have experimented. As I said, there is no one right method. There are multiple other options available. So what we have seen is that there are 3 ways in which you can achieve both AI as well as optimization. So number 1 is by model optimization. The other is using optimized software. And the third is using optimized infrastructure. So we'll look at all these 3 aspects. And again, I'll again repeat this. This is not just the only way. It is one of the ways. So when we talk about software optimizations, we are talking about multiple things here. So first one is it a way that I can optimize and quantize my models in a right fashion to make sure that my compute power is reduced? So what we are talking about here is, and I'll give you a real world example. We were solving we were working for an fintech giant in India. And as you all know, sometimes in India, when you sign up a form, you have to put your picture, and that picture is then compared against a regulatory database. So this fintech company was taking 23 hours to process this particular form or process 1 million forms. 23 hours, and they were using FP32 as their quantization. So by reducing from FP32 and going to int8, we were able to reduce those 23 hours to 10 hours. So imagine the compute time that you were able to save, while at the same time meeting the desired regulatory SLA. Yes, there was a drop in accuracy, but that drop in accuracy was okay to meet those business SLAs. So it's not just about making sure that performance or raw T-flops is my ultimate metric. It is what is my performance per watt? What does my business SLA need? What is my business per dollar that I want to meet? So look at all those angles to make sure that we are able to achieve our objective of solving the problem and yet making sure that the solution is efficient enough. The other example that is about using optimized libraries. So as you know, in the video we mentioned about the One API framework that we have launched. So One API is again an open source based standards, with the idea is to have a cross abstraction across all the different kinds of hardware. So whether it's CPUs or GPUs, from a developer standpoint, you just write your code once and the hardware is abstracted. So this is where when you use libraries such as scikit-learn or pandas or TensorFlows or PyTorch, the underlying libraries are optimized to make sure that they can get the maximum capacity out of the underlying platform. So this is one example of using scikit-learn, where using the optimized library, no code change, absolutely 0 code changes, just using the right version of the scikit library, and again, open source. There's nothing that I'm selling here. You are able to get almost 8x acceleration in compute time and 8.5x reduction in your energy consumption. So those are the small means of using the right software to achieve the sustainability that we just talked about. Last is about using carbon-aware software. Now, there are 2 aspects to use carbon-aware software. One is, let's say if it's a multi-region, multi-country, or multi-continent deployment, so then use the right region which has lower power consumption or which is using the renewable resources of power. But that's very rare scenarios. The other scenario is, when we schedule workloads, when we have clusters of workloads and we are running those workloads, a typical orchestrator will select the node on which to run workloads on a typical round-robin fashion. So what happens when an orchestrator selects a node which is already running at 60% utilization? Now, this is where that specific knowledge comes into the play. So a typical CPU has multiple what we call as P states or power states. The moment the CPU utilization goes beyond 60% or 70%, the CPU starts operating at a higher P state, which means it is drawing more wall power. Because it is drawing more wall power, it is getting heated more, so the fans start rotating faster. Fans would need more power. So there is a net incremental of increase in your power consumption. Whereas the right way to schedule the workloads is to look at the platform telemetry. What is my node utilization? Is there a node which is 30% utilized? Then is that a better place to schedule my workloads? Because if we look at the best way to have a cluster is where every node in that cluster is 50% utilized, rather than having a scenario where one node is 70%, the other is 30%. So this carbon-aware software gets you achieve that kind of a balanced view across all your cluster elements. So the next thing is about hardware optimizations, right? And thinking about what different hardwares are available for running our AI workloads. Now, again, a fun fact, there are only 2 semiconductor companies who submitted the benchmarks, MLPerf benchmarks for GPT-3. One we know is obviously NVIDIA with its H100. The other is Intel's Gaudi 2 platform. The advantage with this Gaudi 2 platform is it's much more power efficient. Yes, if you look at from a T-flops to T-flops comparison, we are not there when it comes to H100. But when you look at what is my performance per watt, what is my performance per dollar, and again, as I said, meeting those business SLAs, meeting those desired objectives, then Gaudi 2 is an excellent choice to run your deep learning workloads. And then, of course, there is the whole CPU aspect. Can I run my workloads on the same cluster which is running my data, which is holding my data, whether it's my Hadoop, whether it is my Spark clusters? So the CPUs also have the capability to run ML and deep learning workloads. Again, as I said, the key criteria is what is those performance per dollar metrics that we want to meet. And that's where we encourage you to look at all those metrics holistically and then decide the right platform for your particular use cases, for your particular requirements. In my initial slide, I talked about the operational carbon and the embodied carbon. So this is one way of reducing the operational carbon. So again, from an Intel CPU perspective, as I was talking about, we have multiple P states. So if the CPU utilization is low and the CPU is working in an optimized power mode, it automatically switches to a lower P state. What that means is there is on an average 140 watts of power saving. Now imagine the scenarios when you are running those AI models, those smart city algorithms during the night time, when the workload is less, when the utilization required is less. By having such a platform which can deliver the similar performance but at a much lower wall power consumption. So this is a clear or a direct result of a lower wall power consumption by just moving the CPU into a lower P state. And as the utilization goes up, so let's say after the off-peak hours, the peak hours come, the load goes up, it automatically then comes to its normal mode of operation and it's able to deliver the required performances. So that's on the infrastructure side as to how we can optimize and get the best architectures available to solve the different problems. The other thing is about data center energy. And as I mentioned in my earlier slide, that a 100 megawatt data center consumes 1.1 million gallons of water. It requires a lot to cool those servers. So data center efficiency is measured by a metric called PUE, or power usage efficiency. Typically, if the data center PUE is let's say it's at level 2, what that means is if I am sending 100 watts to my data center, I'm using 100 watts to run my servers, and then I'm also using 100 watts to cool my servers. That's when your PUE ratios are 2. Typically, what we have seen, at least in Southeast Asia, in our climatic conditions, the data center efficiency is of the order of 1.5, 1.6, which means of the 150 watts that I'm consuming, or 160 watts that the data center is consuming, only 100 watts is being used to run the workloads. 60 watt is being used to cool those servers. So the metric which I showed of thousands of megawatts for running a GPT-3 model, that includes both of the wattage being consumed by those servers plus the wattage being consumed to cool those servers, or the air conditioning, those chiller plants. So now what we have seen is with our PUEs, with our current technologies, we are at the maximum of 1.5 or 1.6. But most countries now are coming with standards that if you want, let's say for example in China, the new rule is if you want to open a new data center, the PUE has to be 1.03. So that means I will get only 103 watts. 100 watts I use for my servers and only 3 watts for cooling my servers. And similar standards are being seen across different countries like in Singapore and in many other countries. So what is it to make sure that we are able to meet those desired PUE requirements? So now there are 2 solutions which are out there. One is air cooling based systems, or how to use outside air to cool your data centers. Let's say in North America, where the temperatures are lower, or even in some Scandinavian countries, when the temperatures are lower, we can design a data center so that it can bring in the outside cold air, and we remove the hot air from the data center. So that can be done. And we have demonstrated that to use natural air to cool the data center rather than using chiller plants or air conditioners. But even with that air-based cooling, the maximum you can go down to is 1.3 or 1.2. We are still nowhere near the required mark of 1.03. So 1.03 can only be achieved by adopting a new standard of cooling called as liquid cooling. And again, liquid cooling comes in 2 factors. One is immersion cooling, where you immerse your entire servers into a specialized liquid, or the other is using a cold plate based cooling. So the equipment is being cooled by passing a certain liquid on certain pipes. The difference between the two is in immersion, your CPUs and GPUs will come in contact with the liquid. In cold plate, there is no direct contact between your server parts and the liquid. There are pipes which are being used to cool down the equipment. So apart from the PUE, what is the benefit of adopting liquid cooling? So the first is density. Now, because we are using liquid cooling, there are no more fans which are needed. So I can pack more cores. I can have more compute in less power space. Okay. The other advantage is reduction in your TCOs, your OPEX savings, your CAPEX savings, because you save on those chiller plants, you save on those air conditioners, and your overall energy requirements come down big time. And last but not the least is, you can capture that heat and use it somewhere else. Obviously, we don't need to cool our buildings. We are already in Southeast Asia. We have enough sun. But we can use that heat to use it for some things like urban farming, to make sure that we are capturing that heat and we are putting it for some use elsewhere. And here are certain examples of customers who have actually used multiples of these technologies to get real advantages. So for example, Siemens is able to use optimized software and optimized hardware that I was just talking about to deliver the same solution at almost 20% less power. Similarly, the big telcos, and as we all know, telcos are a big consumers of compute and for power. So they have been able to demonstrate as to how using AI and how using better technologies, we can reduce the overall power consumption. But with the current AI technology, you know, we have seen the limitations, right? So we know the PUE-related challenges. We know that if we need large language models, if we need multi-billion parameters models, then there is almost a limit as to what or how much efficient that can become. So if we have to solve real-world challenges, if we have to deploy our models in scenarios where we have data, power, and latency-related challenges, there is a new paradigm of computing which is needed. Neuromorphic computing relooks at this entire computing architecture at a transistor level. It is inspired by the brain's biological neuron. Neuromorphic computing departs from your existing computing abstractions, from your existing programming methodologies, to unlock orders of magnitude of advantage in terms of performance and efficiency. So Intel launched this low-heat chip, and we were able to deliver for many of the workloads performance in less than 1 watt. So remember, we were talking about GPT-3 consuming thousands of watts, and here we are able to deliver the performance within less than 1 watts. So here are certain solutions that we were able to achieve with neuromorphic computing. So one is robotic arm control at 40x lower power, and then playing games like Sudoku at almost 2,800 times lower energy requirements, and then scene understanding, which includes a combination of object recognition, tracking, and learning, almost 100x lower power consumption. So this is the new paradigm of computing that we see is set to overtake and meet those requirements of deep learning neural networks so that we can meet those criteria of power and other requirements. Last but not the least, at Intel, we believe it's not just good to be tech zero, we want to be a tech positive partner. So we are working on 4 different aspects. We want to reduce the embodied carbon, as I mentioned. We want to make sure that the operational carbon is reduced by giving certain efficiencies there. We want to make sure that the developers are able to utilize the right hardware and the right software to make sure that they're able to meet those performance and business SLAs. And last but not the least, we want to make sure that we are coming with the right industry solutions like liquid cooling, like other parameters, so that all these new technologies can ultimately help us deliver the desired results. And again, we are not alone in this. We are working with various industry forums to make sure that we take the advice for all the best brains that are out there to make sure that we deliver those desired results. Last but not the least, as I mentioned in my slide in the beginning, it's not just about one view to solve the problems. There are multiple diverse views which are available to solve this common problem of sustainability and to make sure that we are able to meet those requirements. And we need to accept those diverse views. So AI is all about democratizing and opening up and listening to different perspectives, and we believe that Intel is one player in this journey, and of course there are multiple other players who can give and come together to make sure that we are able to meet the demands of developers, business owners, and everywhere. Thank you so much for your time today. Hope the session was interesting.